think we can start, because today we have many speakers, but not so much time. First of all, I want to thank you all for attending this session, especially the speakers. Otherwise, it would be just an awkward meeting. And I hope you are enjoying your stay here in Tallinn. The topic of this session is pavements and road materials. My name is Karli Kontson. I was chosen to moderate this session because my everyday work at road administration is closely related with road materials. Asphalt, mixtures, aggregates, you name it. Our first speaker is also keynote speaker, Professor Terhi Pellinen from Aalto University in Finland, and she is talking about asphalt recycling in Finland.
So good afternoon, ladies and gentlemen. Okay, so there's actually two presentations here from Finland. Tomorrow, Lars Forsten from Lemminkäinen is talking about on Okay, so as we start again, I would first like to thank you for the organizers for inviting me here, actually, and sharing this topic with all of you. And as I was saying, there's two more presentations. So my doctoral student, Mihalina Mankovska, is then continuing some of the topics I'm discussing here, and Lars Forsten from Lemminkäinen is talking about emissions. So what the three items I was going to talk a little bit is what we do in Finland for recycling, basically, and then what are the targets. And if we have targets, then I guess we need to have some kind of a criteria to verify if the targets are met. So we've been doing this over 40 years in Finland, and this hot-in-place recycling is really the working horse for the high-volume roads when we need to fill the ruts that come from the studded tires. And the beauty of this is that we can use 70%, give or take, the old material. We can retain the hard aggregate we've invested for these surface mixes. So it's and the cost is, depending on how much admixture, new material you add, is about somewhere around half the normal asphalt slab. So a few pictures. Here is sort of the convoy, heating elements. This is heated surface. This is how it looks like. Ready surface. Now the admixture has been added, scarified. The heated surface is scarified, then admixture added, rejuvenators added, then it's compacted, laid and compacted, and we have a nice ready surface for driving. So as we add only these 20-25 kilograms, it sort of makes it cheap way to fix the roads for running. But it doesn't add any structural capacity, so that's sort of the key thing to remember, that if we need structural capacity, we need to use something else. So also the problem is that if the road has segregation, you can't really fix it, so you just sort of change the place. And then if there are layers which are separated, maybe you can fix the first one, but then not the second one. Well, none of the methods can do that. You have to dig the whole road up. But if there are any cracks, it fixes that at least for a while. Of course, they will eventually reflect through. But this shows, like Highway 1, very thick pavement, so you can keep recycling. And that's sort of what we try to study in right now for Finnish Road Administration. How can we do the recycling multiple times that we can sort of benefit from the investments we have been doing before by having all those layers of asphalt in the road. So then at low volume roads, if it looks like this, there's no point to do any patching anymore. You really need to do some structural fixing. So what we do is full depth reclamation, where the old asphalt, soft asphalt, is mixed to the base course and maybe some new material added, crushed material, and then you just put it back, compact it, and then new soft asphalt. So this is really a structural method to add structural capacity. And it has replaced basically the stabilization in Finland, so that this is very popular in low volume roads. So then we have this regular asphalt recycling. Site-worn asphalt is processed at asphalt plants and used in the surface mixes. Finnish specification allows to use 50% in surface and base mixes. And then there's this rejuvenation agent like soft asphalt. And the other interesting thing is what we have been trying now is these reclaimed asphalt shingles, the roofing shingles, and then industry waste is mixed and produced this kind of a bitumen mix material that can be used. We tried about 2%. So, of course, we need more long-term performance data, but at least for now, it looks good. There are certain issues that need to be solved here, and one is really, for instance, these shingles, that how they are classified in the specifications. As Finland has been using these recycled materials in Finnish asphalt specifications, it's there. We just updated for the European norms. This new reclaimed asphalt specification that states that reclaimed asphalt is a constituent material that is ready to be used in asphalt mixes, but then there's certain things that you need to sort of declare. One is sort of type of binder, if it's paving grade bitumen, modified or hard bitumen, then you have to declare penetration, where it is, softening point, soft bitumen's viscosity, gradation, of course. So these shingles, the question is now, is it really an additive, or should it be treated like reclaimed asphalt as a constituent material? But the one thing in these recycled materials is that when you use them in the asphalt mix, for instance 50%, the mix has to meet the regular mix requirements, so type testing. And if you change something, you need to do a new type testing. So in situ recycling, this hot-in-place recycling, we do this research now for the road administration to sort of enhance the specifications to allow multiple cycles of reuse for the Finnish roads. So, targets. This is sort of let's say some kind of a flow chart that came up when we did this research, that we have to really decide who is doing and what, because it hasn't been so clear. For instance, this pre-sampling, who takes them, who tests them, and then who makes the plans. So selection of method, is there enough capacity in the road? Of course, that's a road administration, but then a design of targets, what do you have? what should you do, design of application, that's very clearly for the road, for the contractor work, amount of admixture and how to do with rejuvenators, what type, how much. And then there's the work performance, and finally reporting. So there we have to have some kind of a criteria to know that did we met the target. So, well, the idea is towards these perpetual pavements, very heavy base courses, and the only thing we want to sort of do is fix the surface layers. The question is really what we are expecting from the surface layers, that what is the life expectancy. And like in Finland, when we have these study tires, the cycle is very fast, so between 6-7 years we need to go and do the resurfacing. So we really talk about bitumen stiffness when we talk about targets, and then the question is, what do we want from the outcome? Well, in Finland, let's say that in southern Finland, this is very typical surface mix, 70-100 bitumen. So there you see data from actual road 26 kilometers. So you can see that how this is for the research project that we were doing, so that how the penetration is sort of changing. But as an average, it seems to be somewhere there 30, maybe 35, something like that. Well, if you are in France, you actually start from somewhere there 30, 35. And then when this kind of a mix ages, it gets somewhere penetration 18. In India, you start somewhere fairly similar. So where does this end up in the wraps? Well, we had a student from India in our laboratory in the summer, and he brought some samples with him, and penetration 5. So it's sort of interesting that our roads have material that the other ones sort of start with that. But the reason is, again, the climate, that it depends where you are. It depends what your climate is, because you select your materials based on that, and then you have to set up your targets depending what distresses you are trying to prevent. And then comes this interesting question, should we take account the aging during the production? How do we take it account? Do we shoot for virgin materials or RTFOT aged materials? So then when we have sort of selected the targets, comes the question that, okay, what rejuvenator and how much? And we have all kinds of, not all kinds, but let's say 3 different ways to do it, like mixing formulas based on these parameters, one based on penetration, then based on G-star, DSR, and then using viscosity. So there comes the little bit problem that if you think about the alternatives then for rejuvenation, and this is now what I'm talking about, is really hot in place recycling. So we can use soft bitumen, this is very typical. Then we can use, we have been doing some trials for softer bitumens, and Mihalina Makowska will tell you more tomorrow about these trials. And then you can use these oil-based rejuvenators. So as you can see, only viscosity could be measured in all of those. And even in bitumens, the problem is that when you are not in the Newtonian area anymore, how do you do it? Sort of the test methods are sort of time-consuming, tube suction and so forth. So we've been trying to sort of make a shortcut here. As always in a research, you want to sort of, through something more, after you've checked that it works, you sort of want to make it a little bit more simpler. So there's this apparent Newtonian viscosity that it's an empirical equation that was developed about almost 20 years ago in University of Maryland when these superpaid performance models were sort of evaluated. And what it says sort of gives you is viscosity estimation based on G star and sine delta, and then you need to have a correction for this phase lag. Frequency. It's highly frequency dependent because you are not in Newtonian area anymore. So we have DSR testing. So frost breaking point somewhere here, penetration somewhere here, softening point, and then we could also use this for viscosity, but it's in a high temperature viscosity, and we really don't want to be in high temperatures. It's more like we've started to come to the conclusion that we need to be in lower temperatures. So we have selected to do the calculations at 25 degrees Celsius, anyway trying to sort of shoot to the zero viscosity loading times. And if you think about these two parameters, stiffness and then the phase lag is very interesting in a sense that it tells how much the material sort of flows relative that it doesn't flow. Of course, it stores and dissipates energy at the same time. So the more I'm thinking of this phase lag and its importance, the more I'm starting to think that it is very important, because if the material has low phase lag, it means that it's more elastic. It doesn't really flow. And if it doesn't flow, how can it heal? So at high temperatures, if you get cracking, and at low temperatures, if you get cracking, if you can't heal the material, the cracks will propagate and grow. So performance parameters. We found this parameter from the literature, which is sort of relating G-star measurements to the elongation of bitumen in a certain temperature and loading range, and they sort of damage zone that these researchers came up, and then they concluded that they sort of bad area, block cracking, and then good area in the other side, sort of where you can be and then where you shouldn't be. And we took this idea and tried it in our test roads in this very big research we did, and plot the samples, what we had. So here is the samples we took from the before recycling, and then here is the final product that was outcome after rejuvenating the mixes with softer bitumen. So we were in this damage zone, and then we came out of it. But then we did some visual inspection and monitoring of the road 2-3 years, and started to realize that, okay, we came out of this sort of damage zone, but there was still damage, there was raveling. And that came the idea that, okay, maybe in Finland, because the study that was done in the United States, there's different mixes, west track mixes, they are in the West Coast and so forth. So maybe it's something that our mixes are different, and even though we would have exactly the same binder, we wouldn't have the same performance. So combining sort of the idea, this mixture behavior, we developed this additional or a new tone, which is we call insufficient ductility tone. So it's there between this sort of 47 and 180 kilopascal area. So what does it mean? Well, very simply thinking, nothing is simple, but let's say that if we try to simplify it a little bit, it's something that if we are between 22 and 28 penetration, we might get in trouble with raveling and poor performance. So it sort of gives us some indication where we should be when we have finished the recycling work and check that, okay, what we have in our hands. But if you think about now this wrap in France or in India, the India ended up like penetration 5 and the other one was 18. So the 18 is already in the damage zone and the Indian binder is somewhere here. So if you want to use it, I think you need to do quite a lot of rejuvenation. So the other performance parameter we've been thinking is that, okay, this is actually idea I had about almost 10 years ago, more than 10 years ago, I guess, about this performance, mechanical performance, that you have two basic parameters for material, stiffness and strength. And then the question is, which one we need more, stiffness or strength, which is more important? And there's really no answer, because it depends where you want to be and what kind of a distances you want to avoid. So again, are you in India? Are you in Bahrain? Are you in Canada? Are you in Finland, Estonia? It really depends what kind of materials you have, what kind of a structure you have. Some of these are more structural problems. Some of can be maybe related more to the material itself. But if you think about it, material gets from ductile to brittle, and then when it gets brittle, it actually gets damaged. So we have these damage-based performance models and constitutive models. So when there's a damage, you see a decline of stiffness and strength for the material. So if we take this idea, and this is just an example, we've been developing this sort of database for different mixes in Finland. And all these mixes are pavement cores. So that's why we use this indirect tensile test there for both to measure the stiffness and strength. And we use 10 degrees Celsius to sort of capture the low temperature performance. And what is sort of interesting is that there is no correlation, as there shouldn't be, because as you can think, with different stiffnesses, depending what kind of a binder you have here, you still might have the same strength for the mix, or other way around, that you have the same stiffness, but then you have a huge variation in the strength. So what is driving what? Air voids is driving this one, because air has of course no stiffness, but no strength. So really the air voids is driving here when the stiffness is driving here, coming from the bitumen. And if you think now this idea from ductile to brittle, so we are really going from here to here. And why I have this red box here is that I think that some of these mixes, and this is actually proven from the research we did, is that you are actually seeing something like this. It's not that you have a soft material there, but it's so cracked, it's so stiff and cracked that it doesn't have any more good strength. We had some samples here that we couldn't even test because they fell apart when we took cores. So somewhere here we think is the good performance, and we are trying to sort of find the values for the finished mixes that we could then set guidelines and sort of evaluate our rehabilitation of materials. Thank you.
Thank you, Terhi. Excellent presentation. Does anyone have any questions to Terhi? I have one question, Terhi. How many passenger vehicles are using starter tires near the Helsinki region?
That's a hard one. Last time we did some research, it was in Helsinki area, actually city of Helsinki tried to sort of, they want to sort of reduce the use of studded tires, and they did the research somewhere around maybe 70%, but then the results were sort of mixed, and they didn't go to any restrictions, even they were sort of wanting to do it. But Helsinki has lots of hills, and then the argument was that if there wouldn't be studded tires, the roughening the roads and giving you the friction, the other ones, you know, all wheel tires couldn't run. So it's unsolved question.
Okay. Thank you. Our next speaker is Matas Pulevičius from Lithuania, and he's going to talk about using granite fillers in asphalt mixtures. Mr. Matas?
Hello, everybody. Dear colleagues, my name is Dr. Matas Pulevičius. Today I'm representing Milsa Group, that is one of the biggest crushed stone suppliers in Lithuania, and I want to talk about good practice in Lithuania of using granite filler for the production of asphalt mixture. So actually for a long time period in Baltic states, we used only lime stone filler for asphalt mixture. However, in Nordic or other advanced European countries, they use also igneous rock fillers, and it is really successful practice. So to follow that good practice and to solve some environmental problems in Lithuania, joint stock company GRANITE initiated actually research study, and independent laboratory started testings for suitability of granite filler for the asphalt mixture. And in 2016, one of the biggest asphalt producer, Eurovia Lithuania, started to practice to use granite filler in asphalt mixture. So in this presentation, we will talk about the problem, which is the main thing, what we have to solve. Then we'll talk about the mineral filler purpose and function in asphalt mixture. We'll do it shortly. Also, I'll show the simplified scheme of a production of granite filler. We'll talk about characteristics and actually the analysis and statistics of asphalt tests, and we'll finish with conclusions. So granite fine actually occurs already in process by blasting, by clumping, crushing, and friction in between during transporting. So it already comes, part of it comes with a raw material in the factory. And later in factory, we also do have some processes as sieving, some natural process, another process, and it also occupies some part of granite fines. So the product, the granite product, is being washed, and all that fines goes to sedimental pools, and later they transport to some special open area storage places. So if to talk about the problem, the amount of problem, we can say that approximately granite fines make about 70 kilograms per ton of a granite production. So if you believe the Lithuanian statistics, in between of 2013 and 2016, the granite of a fraction 0 to 16 market took about 1,250,000 tons. So it makes about 312 tons per year, and it makes around 22,000 tons of a granite fines per year. So what would you have? Without any additional processes, granite fines is treated as a waste. So what we do have with the waste, we have utilized it or just stored in some special storage places, and actually it is quite expensive. And to talk about utilizing the granite fines, personally, me, haven't heard any solution for utilization. So if we talk about the industry in a global and about the crushed stone factories in this particular situation, our aim and goal is to have waste-free production. So by following this aim, the joint stock company GRANITES established a granite filler production line and certified granite filler product that product for asphalt concrete, for concrete and mortar. So just a short, or maybe nothing extremely new, but just want to point you that the mineral filler is the most important structure in asphalt mixture composition. Because its area comprises around from 90 to 95% of all total area of a mineral filler. And what we do want to talk about is about the adhesion. So to talk about the long life of asphalt as a production, as a product, we need to have it as much as we want to have it in good quality. I just want to show you just a simplified scheme of a production of a granite filler. So from a bunker, it is weighted and transporting to a dryer, and later in a separator with the help of a centrifugate force, it's separated to two parts. The parts that is upper, then a 63 micrometers, and everything that passes. So what passes is a final product, and it goes to a special storage bunker or just right to a big bag. Here you see declare values of parameters of granite filler. Actually, it all satisfies the requirements of asphalt mixture, mineral filler. And to show you the stability of production, I just put some histograms of, in my opinion, most risky values that result has a most bigger frequency during producing processes. So it is the passings through 125 micrometers, passings through 63 micrometers, and water content. So as you see, they are strict in between of requirements limits. And if to talk about the practice of in Lithuania to produce that asphalt mix with a granite filler, we have some results from a control testing laboratory that is independent. And in this multi-histograms, there are several values that shows is the asphalt mixture does the asphalt mixture satisfies the approved asphalt mixture or not. So you can see a difference in can see. Yeah, the first one is a difference in a bitumen binder. So only one sample from 106 didn't satisfy the limits. The 98% satisfied requirements with different in air voids. And all samples satisfied the requirements for passing through 63 micrometers, what shows the right amount of mineral filler. So what the main thing that shows quality of asphalt as a product is the compaction ratio. So from all 4 mixes, what I want to say that top layer mixer, inner layer mixer, SMA mixer, and base mix, only 3 samples did not satisfy the requirements. And it might be several reasons, maybe some weather condition or some technology. So to talk about the conclusions of this presentation, I want to say that the granite finds aqueous production due to the different processes, and it takes around 7%. So we have some kind of waste, if not to make some different and special process to make him and use somewhere. So the goal of our production is waste-free production, and this waste we can certify it and use for something useful. Also, the production and science do not yet have a clear answer on the asphalt concrete mixture, mechanical and durability, mechanical strength and durability. The practice of using granite filler for the production of asphalt mixture during 2016 has shown that this product does not impair the quality of an asphalt mixture when comparing its quality to conventional mineral filler. And physical mechanical properties of a recently produced asphalt mixture and pavement made from it are determined by the applying classical standard testing methods. So the absolute values of these indicators show the suitability of a granite miller fillers for the production of asphalt mixture. So it's all I wanted to show you with my, I believe, short presentation. And if you have some questions, with pleasure, I will try to answer you. Thank you.
So any questions?
My name is Heikki Alang and I'm from Lemminguinen subsidiary here in Estonia. And I would like to ask, have you checked during this tests also the chemical composition of this mineral filler?
Yes. Yes, we do have. As far as requires the European Union norm. So we did the chemical analysis.
I didn't saw the name of Lithuanian Road Administration among of participants there. Do you know, and can you comment the attitude of Lithuanian Road Administration to the results? Thank you.
I think we should ask for a road administration representative, but as far as I know, road administration look to a quality of a road just in the limits of norms, and if it's as far as satisfied, it's okay. As I showed in my last slide, I believe, it was written that only standard testings shows the quality of asphalt, and actually for purpose of to know the real thing, we have to make some different tests that are not standard. It's my own opinion.
I have a question. Yeah, Simon Hess from Canada. In Canada, we use hydrated lime. We add it to mixes that are susceptible to stripping. And it's basically because it's basic additive. It neutralizes the acidic components in the asphalt cement. So the granite filler, is it acidic or is it basic? And what do you expect long-term performance? I guess that's the issue. After for 10 years, do you get any problems, or do you anticipate any problems from the fact that it's a different basicity or acidity? Do you anticipate any problems long-term from the fact that it is not a basic material? In North America, they add a basic hydrated lime because it's basic.
As I said, to look to a long-term life of asphalt, it passed only 1.5 years, so we didn't do any testings, but the quality of asphalt is
looks the same.
Yes.
But is it acidic, the filler that you're adding, the granite filler? Is it acidic, or is it basic, or is it neutral?
No, it's not. You you are asking about pH.
Yes.
It's less than neutral, a bit less than neutral. Yeah, because it's granite. It's not lime.
So it's acidic.
Yeah.
Yeah, so you have to be very careful with the long-term durability when the oxidation of the asphalt binder produces more acidic components that cause stripping. So you have to be very careful with that, I would say.
As I heard, you are from Canada.
Yes.
So what is your practice? Maybe you have some norms that somehow requires to add some.
As I mentioned, in all the high-quality freeway mixes, the surface courses, we have to treat it with lime, because it's a basic additive that neutralizes the oxidized product from the asphalt cement. So that's done 100% of the time, because it's a very expensive failure when it starts to strip. And it only shows up later in life.
Thank you.
Thank you, Matas.
Thank you.
Our next speaker is Henrik Puhkin from Estonia, and he's going to talk about using oil shale byproducts in road construction.
Good afternoon, ladies and gentlemen. My name is Hendrik Puhkim, and I will tell you about the Osamat project. This was a project where we tested oil shale ash as one material in road construction. The owner of this project is Eesti Energia, who produces as a byproduct a lot of oil shale ash from its power plants in eastern Estonia. So we tried to give some additional value to the material with this project. This project was implemented together with construction company Nordecon and Estonian Road Administration, and co-financed by European Union fund LIFE. So first I will tell you shortly about our company, as we acted here as a consultant and engineer during the whole process in this project. And we are Skepast and Puhkim, environmental, land use planning and infrastructure engineering and consultant company. We were established in 2006. Back then we had a different name. It was Rumble Estonia. But 2 years ago, together with Peter Skepast, we did a management buyout, and now it's called Skepast and Puhkim. So we have 35 professionals working in our company, and last year we had about 1.8 million euros turnover. So back to Osamat project. This project lasted 6 years, from 2010 till 2016. So I tried to tell you 6 years in 15 minutes here. So very briefly, the project cycle. So first, we did a lot of work behind the desk. We did the project plan, planned different steps, how to do it. Then we did field research on site. We did a lot of laboratory researches in Finland, together with Rumble, Finland. Then in this project, the actual 2 pilot sites were built in Estonia, followed with technical monitoring and survey, how this construction came out. So I think we covered all the logical steps to find out does this work or not. I have to go back to history, as during this project it was asked many times that why are you bothering again with this oil shale ash? It was tried in 1970s and 80s, and it didn't work out. Everybody knows that. So why again this waste of money and time? And I think I should explain briefly why we did it again. It is true that in 70s and 80s, yearly some 100,000 tons of oil shale ash was used in road reparation and in agricultural industry. But the difference from today was that, for example, the dosage accuracy was not so good, so the material was used, if you may, how it happened. And there was no special machinery to do the work with oil shale ash back then. And also the amounts of oil shale ash, we can say today, were much too big. And one thing what we did different in this project that was not tried before in Estonia was mass stabilization with oil shale ash on existing road. So this was a new thing, and I think that gives a difference in this project. So we had two pilot sections in different locations in Estonia. First of them was on Narva Mustaja road section, between two power plants. There was 1.6 kilometer long road section where we tested different oil shale ash qualities. It means that we had different thicknesses in layer stabilization. We tried different oil shale ashes. We sort of played with the amounts of oil shale ash and cement in the mixtures. So we had altogether seven subsections. We did a lot of quality control activities in this section, and there was water content testing, compaction measurements, unconfined compressive strength testing, freeze-thaw durability testing, and load-bearing measurements. So I will talk some of them to you. Unconfined compressive strength testing is a very typical way to find out how this material resists to a force. So we took several samples to laboratory and showed some force to them, and to find out how strong they are. And secondly, we did classical freeze-thaw durability testing in the laboratory. So on this table, you can see the results, for example, from about 30 days after the construction. And according to our knowledge and previous experience, numbers over 1 are okay, numbers over 3 are very good, but the numbers should not exceed, for example, 12 megapascals as it comes too strong. So here you can see that all numbers are showing a good result, maybe except this section here, which was done with cyclone ash. So it didn't work so well, but still good enough. And then we had this freeze-thaw durability testing, where we basically took the samples and put them to freezer, then took them out, melted them, then put them back to freezer, took them out again, and did it several times. And after that, we did this compressive strength testing again. And the idea was to check how the samples are resisting our weather conditions as we have them. And here you can see the results of the freeze-thaw testing, and the decrease of the resistance was about 15%. So this is considered as a good result. Then we did load-bearing measurements 3 years in a row. Sorry. We set 260 megapascals as the target value for us. And you can see that all the results during 3 years were over this target value. Some of them a little bit over, some of them a lot more over. Some numbers showed even 600 megapascals. Then the second road section. This was Simuna-Vaiatu in Lääne-Virumaa. It was this swamp or wet area, but on an existing road, where the main purpose was to try out the mass stabilization works with this layer here. So this is the peat layer, which was mixed with oil shale ash material, and it was about 1 meter to 3 meters thick under the road. And we tried different binder recipes with different oil shale ashes. We tried cyclone ash. We also tried 2 other ashes from the so-called newer burning technology boilers. And we added also some cement to the mixture, because the laboratory results showed that oil shale ash alone does not work so well. And about quality control actions, there was 3 main actions. First of them was XRF analysis. Then we did cone penetration and vein shear testing, and then we measured how the layer is settling after the mass stabilization works ended. So XRF means that we had a calibration mixture prepared in laboratory with the optimal and ideal content of calcium in it, and we took several material samples from the site after the mass stabilization mixture was done, and we measured the concentration of calcium, and the purpose was to get numbers as close as possible. So you can see that they were quite close enough, and this is just one example of the results. We have long list of them. And the method was very simple. It was done with portable machinery on site, very fast and effective way to find out the results. Then we had cone penetration and vein shear testing. This was done also in different locations. First of them some 2-3 months after the mass stabilization works ended, and the idea was to find out is the stabilized layer become uniform and homogeneous enough. And we set ourselves a target value 50 kilopascals. So, and we did the second cone penetration and vein shear testing about 1 year after the stabilization works ended. So, and the results showed increase of the uniformity and homogeneity of the mass stabilized layer. Then we measured how the stabilized layer is settling. For that, we installed 5 metal plates on top of the layer, and we put 1 stick into it to measure the height in different places. And we found out that in about 1 year, the settlement was some 4 centimeters, which is okay, also based on experience in Finland, as this was done on an existing road. When it's done in a completely new road, of course, the settlement is bigger. The numbers are bigger. This was a pilot project. So one of the ideas, at least to my mind, of a pilot project is to know all the possible challenges that you might have when you are doing an actual project later on. So we had, for example, cracks on a Narva-Mustamäe road section, and we think it was because of the shrinking effect of the stabilized layer. And one recommendation for the future is to cut some joints to the pavement to avoid this kind of cracking. Then we had problems with oil shale ash in mass stabilization site. We had some inconsistency in the material. There were some small stones inside the material which were blocking the tubes. But we now know it, and Eesti Energia, as the producer of this material, can make some adjustments into its technology. I think the main challenge here is that there is yearly 6 million tons of oil shale ash coming out of the power plants in Narva. So there is a lot of unused good material. Thank you.
Thank you, Henrik. Interesting presentation. And since you were right on time, we don't have any room for questions. So our next speaker is Marta Wojcik-Wisniewska. I hope I got it right. Estonian, sir. Ah, you changed. Okay. So you can introduce yourself. So the floor is yours. Thank you.
Hello, everybody. My name is Krzysztof Błażejowski. I work for Orlen Asphalt. The author of this presentation is Mrs. Marta Wójcik-Wiśniewska. However, the presentation will be done by me. Short agenda of my presentation. The first, some introduction of our company, then introduction to the problem, then some results and description of the problem of physical hardening, and then low temperature properties of asphalt mixtures, and then some test results and conclusions. Orlen Capital Group is one of the biggest companies of Central Europe. Its assets are in 3 countries, in Poland, Czech Republic, and Lithuania. We operate, frankly speaking, and very shortly, almost 3,000 petrol stations, and commonly we are recognized as a producer of the fuels. However, we produce many other products in refineries, but also in petrochemical sites. Orlen Asphalt is a part of PKN Orlen Capital Group. We operate production and selling of bitumens in 3 countries, in 2 refineries in Poland, 2 refineries in Czech Republic, 1 refinery in Lithuania. And since 2012, we operate also in special place for refueling and selling bitumen in Romania. In each place, we offer many bitumen products, mainly paving grade bitumens, which are the most popular products in this part of Europe. However, in 1 refinery, we also offer multi-grade bitumen, I mean the refinery in Czech Republic, and many places also offer polymer modified bitumens. After this short presentation of our company, I want to take an introduction to the main topic of the subject. Everybody knows that bituminous binders are the thermoplastic materials, and therefore their properties depend on temperature. However, the most popular properties of binders and then asphalt mixtures are rotting resistance. And in Poland, for many years, we were fighting against rotting. And then we know that what resistance to rotting means. It means that we should use the better aggregate skeleton, and it means that we probably use stiffer, I mean harder bitumens. And if we think about rotting resistance, it is okay, but from other side, we should remember that we have also winters, and at winter time, there is some other type of problems. I mean over-stiffening asphalt layers, and then some other problems could occur. At low temperatures, the most important factors having a destructive effect on asphalt mixtures, using especially in wearing courses, can include thermal shrinkage of the binder and asphalt mix, physical hardening, stiffness of or over stiffness the courses, action of freezing water, or action of de-icing agents. We know that usually there is not only one factor, but at winter time we have, let's say, the sum up of all factors. And what is important, those factors don't work identically throughout the low temperature range. We know that the asphalt mixture behaves in different way close to zero when the water is freezing, and different way in its very fast drop temperature of the temperature, and in other way if the low temperature is during the very long period. Frankly speaking, the bitumen industry for the long time is looking for a method how to evaluate not only binders but also asphalt mixtures. And as I said, when we look at the rotting resistance, the problem is solved. Everybody knows that in European standard for rotting resistance there is almost 4 testing methods. But when we think about low temperatures, there is no so clear situation. So we wanted to select raw materials we used for bitumen and polymer modified bitumen production. So we decided in the past in our research program to use for the first time the Canadian method LS308. It is sometimes called extended BBR method. This method determines the what degree bituminous binders are stiffened as a result of physical hardening. The physical hardening is, let's say, one of the topics of this presentation. And I would like to describe this phenomena the next slides. What we think about physical hardening, it is a phenomena which takes place during the long-term storage at low temperatures under isothermal conditions. We cannot join it with fast dropping of temperature, but we should think about it as a state when the low temperature is steady and very low during the very long period. During this period, we can observe the increasing the stiffness of the bituminous material, and stresses are generated inside the binder, and then it could lead to thermal cracking. What is important, the scale of this phenomenon mainly depends on the time for the thermal stabilization. Simply speaking, the longest period with low temperature, and the properties of the binder. What is also important, the physical hardening is a reversible process, and after warming up the sample, the properties are recovered. when we talk about the properties of the binder, so there is some interesting factors which influence on the behavior of the binder. We can say that it is a chemical composition of the binder, a crude oil source, production technology, use of additives, polymers, some chemicals. We can say that there is a lot of different additives and technologies how to produce unmodified bitumen and also polymer modified bitumens. And physical hardening of bitumen and then potential changes of the properties of asphalt mixtures can have an influence on the behavior of road pavements at low temperatures. And at this point of view, we are fighting against low temperature cracks. Some slides about the LS308 method. The method is based on BBR equipment and is starting from the same rules as BBR testing. Probably you know from the super pave system, which is very popular in North America. But what is in addition to this typical test, that we introduced to this test freezing, conditional period. And after specified time of this conditioning period, especially after 1 hour, 24 hours, 72 hours, the stiffness of the samples are measured, and then based on calculations which are very detailed described in the standard, we can calculate the final assessment of the binder, which is called grade loss. As I said at the beginning, and what is important at this moment, this is those results I will show you are part of our bigger research project, which was focused on selecting raw materials for production of pure binders and for polymer modified binders. Unfortunately, we use at that stage of this project mainly hard bitumens, because as I said, in Poland they are the most common used products. But when you can see on this table, on this chart, the penetration of the products of the bitumens are between 30 and 60. So, let's say, starting from the beginning, there are the very hard bitumens. And on the former presentations with this professor from Finland, we know that it is not the best idea to use such hard bitumens in low temperatures climate. At this moment, we use samples produced in the laboratory. We selected some components as raw materials, which were suspected to be with negative impact on physical hardening of the bitumens. So, as I said, we did this test for the first time ever in our laboratory. So we expected that with selecting such raw materials, we had to see real effects. So the second our goal is was that we wanted to check how polymers behaves in the different base bitumens. And what is well known that physical hardening is very common thing in polymers. So it was a question, what is the possibility to see physical hardening in polymers and the pure bitumens. Some results. The first, the table with temperatures of conditioning, of freezing the samples. The base is, according to this method, low critical temperature from superpave method, and then according to this we calculate the freezing temperatures. And some results, unmodified bitumens with special, let's say, raw materials. We can see that during the first 24 hours, the stiffening is the highest level. Then between 24 and 72 hours, the stiffening is not so sharp. This is similar for polymer modified bitumen. You can see that in this polymer modified bitumen, which contained a special mix of polymers. We tested it, how it behaves, and we can say that we can say that it is a bad idea to use this kind of polymer. Then we tested asphalt mixtures according to well-known method, TSRST. This is a method not especially for physical hardening, but for thermal shrinkage. And for this purpose, it is a very good method. And results, they are the same laboratory prepared samples. You can see that there are visible three groups: unmodified bitumens, modified and highly modified bitumens, and then temperature of the cracking. There are also three groups with the special superior result of highly modified bitumen. Some correlations. It's very simple to answer. There is no correlations. And some summary of this presentation. Physical hardening is influenced by the temperature and temperature at time of freezing time of bitumen. It is obvious that the lower the temperature and the longer the freezing time, the greater effect of physical hardening. What is also visible, it is with very good agreement with other publications about this subject. The greatest speed of stiffening is observed in the first 24 hours of freezing. So we could say that the first day in very low temperature is the most dangerous for the wearing course. Highly modified bitumens, due to the very SBS content, by mass more than 7%, but by volume more than 50%, is characterized by the lowest LCT and highest resistance for physical hardening. It is very interesting information for us because it means that the polymer used for HYMA is a very good polymer. And TSR is probably very good test, but it shows only one side of low temperature behavior. Maybe some changes in the method could change the usefulness of this test, to use it in assessment of physical hardening. And I can say that we will continue our test because, as I said, it was the first shot we did. But for sure we will change some method in TSLST and some also freezing parameters in extended BBL. Thank you for your attention.
Thank you. You only have time for one short question. So, thank you. Our next speaker is Carl Robertus from Sweden, Nynas, and he's going to talk about what happened to bitumen in Europe.
Thank you very much for the opportunity to speak here. The title is What's happened to bitumen in Europe? There will be three parts to this presentation. One, I will tell a little bit around the supply and demand of bitumen in the past. There will be a little bit around the development of specifications in Europe around bitumen. And the last, third part, is around some new developments and thoughts and concepts to describe the long-term durability of bitumen. And hopefully at the end of the presentation, you will understand that bitumen is not just black, but there are many shades of black. In since 2000, a lot has happened with bitumen demand, and it is in the last 10 years, it has declined in Europe by approximately 30%, mainly due to the economic downturn, of course. But there are also big regional variations. Average 30% down, but there are areas where bitumen demand has dropped by 60%. But there's also areas where bitumen demand has been stable or seen some growth. And with these big changes in demand, of course, the supply landscape has changed and has developed. And the supply landscape, because bitumen is produced in refineries, you have to look at the refinery landscape. Where is bitumen produced in Europe? Well, during this 15 years' time, refineries have rationalized, have changed. Refineries have disappeared. The number of refineries has dropped from 130 or so have disappeared from the map. And dropping also the crude processing capacity in Europe. Today, we're producing bitumen in approximately 55 refineries in Europe. But the number may change in the near future still. Because of the changes, we can safely say that bitumen is traveling further today compared to what it was 10, 15 years ago. And as a consequence, our customers may see some further variations from a quality perspective of bitumen and the source of the material. On a positive note, I think it's important, we've seen since last year that bitumen demand seems to be increasing moderately again. And it's also important to understand that bitumen production capacity looks like it will be sufficient to meet the demands in the future. But of course, being a seasonal product, there will be ups and downs, and during the season there might be some tightness in bitumen availability. Now, bitumen in Europe is regulated through the Construction Product Directive. Bitumen is specified for roads, and today it is specified generally in traditional specifications, empirical test methods. And really one has to ask yourself, are those materials that comply with traditional empirical test methods, are they suitable for all of today's applications and all of today's circumstances on the road? Now, since the introduction of harmonized bitumen specifications, and these specifications, like I said, they consist of pen, softening point, traditional test methods. Now, since the introduction of harmonized bitumen specifications, there's been quite a lot of research done in Europe and outside of Europe to look at and understand bitumen deeper and better than looking at just the standard empirical test methods. And I've given in the following a little bit some milestones around what has happened during what has happened in terms of research around bitumen, and moving from empirical specifications to more performance-related specifications. And moving towards performance-related specifications is important because that is what the regulation today in Europe is. We have to use performance-related specifications rather than empirical specifications. Now, all this research has helped us at least to understand a little bit better the rheology and the behavior of bitumen and how it works in the field and in the lab. And it's important to meet those performance specifications because the demands on roads have changed. And the demands on roads have changed. They've become more traffic, there are higher demands, and we are required to build our roads using sustainable methods, longer life, and durability. Now, what does that mean for quality, for bitumen quality? Today, we are still talking, when we're looking at the majority of standard paving grade bitumens, they're specified using traditional test methods, and they're specified using an aging method which tries to simulate the short-term aging of bitumen. However, we know that our roads have to last longer. We know that the bitumen has to last longer, so we have to look at long-term aging. And recent research from outside of Europe has shown that there are some failure phenomena that occur on roads that are not so much related, cracking type phenomena, that are not directly related to temperature or traffic, but are more related to the aging of the asphalt surface and consequently the aging of the bitumen surface. And in 2011, there was a paper published by Mike Anderson, and it demonstrated, they looked at some of these phenomena. They looked at these phenomena that are where short-term, after a few years, cracks and raveling started to appear on the asphalt surface. And they tried to link that to the rheology of the bitumen. And two parameters have been important in looking at that research. One parameter is called delta TC, and the other parameter, Professor Pellinen has already mentioned, the Glover-Rowe parameter. I will focus on my presentation in delta TC, but I will make a little mention on Glover-Rowe parameter as well. Now, why is this important? It's quite important because last year, Jerry Renke and his colleagues, they published a paper at the Eurobitume conference, and they showed field performance. Basically, they looked at cracking of field sections, and they compared that to the delta TC of the binder recovered in the pavement. And you could see that delta TC was an important driver for the cracking of these field sections. So it's quite important to see that there's a link between the performance of the asphalt and this particular parameter when it comes to bitumen. Now, how is that relevant for us? Well, in Europe, we don't have a bending beam specification currently in our specifications for standard grade bitumen or polymer modified bitumen, but we do have a test method. We've taken the test methods from the US and to understand better the rheology of bitumen. And in this example, we've tested 5 different bitumens, which are quite common bitumens that meet the European specifications, bitumen A to V. They're all roughly, one is a 40-60 grade, the rest is a 50-70 grade. And we've done bending beam tests on these materials. And in the bending beam test, you test basically 2 critical parameters. One parameter is called LMT, that's the stiffness, the limiting stiffness for relaxation, which is basically driven by the slope of the stiffness versus temperature curve. And the second parameter is LST, which is the limiting stiffness parameter. Now, these 2 parameters are integral part of the superpave specification. But what is new and what they've discovered is that this difference between these 2 parameters, delta TC, is quite important. And it is this parameter that seems to be driving some of the durability failures on the asphalt pavement, and therefore this parameter could be a parameter that says something about the durability of the bitumen. Now, this parameter is not measured on fresh bitumen. In actual fact, this parameter is measured on bitumen that has been aged, not just short-term aged, but also long-term aged. short-term aging is part of the European specification, but long-term aging is not part of the European specification for bitumen. Now, aging. Aging is not a property of a material, but aging is a process. And just to give you a little bit of an idea of such a process, I've tried to build an analogy with some musicians. And some may recognize these two musicians at the beginning of their career, about 40 years ago, hopefully also the lifetime of General Bitumen. Anybody would like to guess who that is? Who these two people are? Perhaps if I show you shortly after their career has started, short-term aged, you may be able to recognize them a little bit better. 40 years in their career, recent pictures, you can see the long-term aging of these two individuals that have been exposed to a similar environment and a similar climate. We see that the end result is very different. Some may say that the lady on the left is highly modified and the lady on the right is standard bitumen, but I beg to differ. So we've looked at a number of standard bitumen and we've looked them in a short-term and long-term aging step. And we've measured delta TC on these 5 different bitumens, A to E. You can see that on the fresh bitumen, delta TC is positive. It's roughly the same. Some are a little bit better than the other. But generally, you can see there's not much difference between these materials. But on the yellow bar, this is after short-term aging and long-term aging of the bitumen. And you can see that there are remarkable differences in delta TC. I've drawn 2 lines. I've drawn a green line, which is 3 degrees, minus 3 degrees, and minus 5 degrees. The minus 3 degrees corresponds to the notion from the field that is where bitumen starts to crack. The minus 5 degrees, if you are below minus 5, there is serious risk of bitumen cracking in the pavement. Now, how does this look when I look at it in a broader context of European bitumen? These are 5 bitumens, and we thought that's quite interesting. We see remarkable differences. But what about other bitumens that are available in the market? And we know that because of the work and the research and development work that has been done over the years to try and understand more about the rheology, there's quite a lot of rheological information about bitumens in Europe available. Eurobitume has produced a database of about 168 bitumens that look at the bitumens in a traditional way, empirical sets, but also look at the material on a rheological scale using new test methods. Now, the next graph I've presented a little bit colorful. I've presented along the x-axis basically short-term aging in terms of changes in the softening point of a rolling thin film oven test on a standard bitumen. This is part of the European specification. If the bitumen changes in softening point is less than 8 degrees, it's okay. It conforms to the specification. If it's between 8 and 10, it depends a little bit on the grade, whether it meets the specification. But if it's more than 10, you're outside the specification, so it's red. On the y-axis, I've given the delta TC, whereby anything below minus 3 is, anything above minus 3 is okay. Anything between minus 3 and minus 5, there's a risk of cracking. And anything that is above, let's say below minus 5, there is a serious risk of cracking. These are the 5 bitumens that we've tested. And you can see they all meet the short-term aging test, but you can see already there's a difference in terms of delta TC, and therefore would expect a difference in long-term aging behavior. Now, these are just the 5 bitumens from our experiment, but we've plotted, let's say, from the databases that we have available, we plotted the number of European bitumens. And this is what you see. It's quite striking. Most of the bitumens meet the short-term aging requirement, but the differences that we see in these materials when it comes to delta TC, it's remarkable. Some materials go down to minus 17. And these are really materials that are at severe risk of cracking early life in the pavement. This is a data set that contains both modified bitumens and standard paving grade bitumens. So it's quite a remarkable difference in the performance in terms of long-term aging resistance compared to short-term aging resistance. We've done a similar, when we talked about delta TC, we've also looked at these materials in Glover Row, and Professor Pellinen has already shown this picture. And we can plot those 5 binders that we tested in the laboratory as well. They look very much the same. They start at the bottom right-hand corner when they're fresh, not aged. But when you start to age these materials, you will see they go up, move into the cracking area, and here you can see that the bitumens A and B that perform the best in delta TC, they remain in the area where there's no block cracking, while the bitumens that show a high value of a high negative value of delta TC, they are in the blocking area. So, concluding, bitumen travels further nowadays, more than it used to be, and it does give a diversity in source and supply, and also in supply chain operations. The specifications today, they have to be performance-based, and that must include long-term durability. We see when we look at published data, there are wide variations in delta TC of bitumen in Europe, so really long-term performance is expected to be very different. We need to have further work to validate the concept of delta TC, but I think it's important when you're selecting the bitumen for your asphalt application that selecting the right bitumen for that application is important. So, hopefully, bitumen is not just black, but there are many shades of gray. If you have any questions, please come and see us at the stand.
So, thank you. This presentation concluded our session, and I'm not the guy who's standing between you and coffee. So, thank you.